Okay. Then let's continue now. If object try to rotate the direction, what will happen? Object will become imbalanced like that, right? It will go into the position like that. If I want to bring it to the balance, what you have to do, you have to apply another force right here. Let's say I have a mass M2, and then the distance from here to here, let's say x2. If you apply that mass M2, if you look at the free body diagram, then I have a force of gravity right here. That's going to be M2G, which is F2, which is actually x2 distance from this point P. So which means that force will create torque on CCW direction. That will be the torque acting around point P on left hand side. So that is equal again R cross F. R is x2, F is M2G, and then angle between them sine 90 is 1. Direction of that rotation is positive k hat. So I have two torque acting on the object now, right hand and left hand direction. If I have these two equal, what will happen? Net torque going to be 0. If I create this torque of P right direction equal to the torque of P left direction, if these two are equal, so which means sum of all the torque around point P going to be 0. If that happen, we know there will no rotation at all. If there's no rotation, then we can say object come back again to the equilibrium condition. So that's the idea. That's what actually we try to investigate in this experiment, just creating a larger object. Now this is the free body diagram. Earlier I mentioned that free body diagram is same. The free body diagram is slightly different for when you go into the chapter number 12. This is the idea. That's the free body diagram which we're going to draw in chapter number 12. Not the free body diagram we are drawing so far. So far, when we're drawing the free body diagram, we're interested to show all the object starting from the origin and then on XY plane. Now, XY plane is still there. Okay, nothing difference in terms of XY direction is still hold. This is Y, this is X, and then this is Z. That coordinate system is still there. What difference is that now we don't put origin and then all the forces. There usually we put the origin exactly the fixed point. If there's a fixed point, we assume that's the origin point. And then relative to that, this is positive X direction, that is positive Y direction, that is positive Z direction. And then relative to that origin point, I have to show, because now the object is elongated, I have to draw exactly the forces acting which location, because this R is key to understand this situation. R is actually displacement from the origin or the fixed point to the force acting point. That's very important to understand which direction is this torque is actually happening. If I don't know that, then I can't really understand this situation. Okay, so that's why the free body diagram, keep that in mind. So far, until this point, you don't need to worry about drawing free body diagram this way. But when we go to chapter 12, I will remind you that free body diagram should be look like that. Otherwise, it has no meaning. This is the part which is actually going to be connecting to the PHY 294 class. Okay. If you are planning on that in terms of, even though it is under PHY, this is not a physics class, it is actually engineering mechanics class. In terms of physics, you actually need only this, that's all. In terms of physics, there's no physics on that class, okay? So in terms of physics, what you really need, the understanding of the how to figure out the equilibrium of the object. So that concept going to be taking and then applying into the larger structure. That is why that class is key to actually civil engineering and mechanical engineering, because you have to understand, especially in the civil engineering, how to stabilize the larger object. If you want to do that, you have to understand what are the torque acting on different places. Then you have to do, for example, if it is a large bridge or building, something like that, you have to draw this kind of larger structural free body diagram. And then on top of the torque, only thing you may need for that class is the idea of the elasticity, There are concepts actually with the elasticity little bit. So those are the ideas you actually needed for that class. Okay, that's why that class itself called engineering mechanics. Technically, you're talking about the stability of the object under various stress and strain. That's all. Okay, if you are planning on doing it at some point, it may be a required class if you planning on going into the mechanical or civil. I think in future. Other engineering, that class actually has no meaning at all. All right, any other question? Okay, then let's continue. Now that's the idea. So in this experiment, so technically what we're trying to do is actually trying to understand the equilibrium of the object by looking into the Fibber diagram, how it's gonna change its equilibrium, and then accordingly how we can balance that object again. Okay, bring back to the equilibrium. Okay, that's the plan. Any question? All right, then let's continue. So in terms of theory, that's why it's nothing much, right? Just the torque equation, that's a theory. And then right now, by now, you should have some idea. So I explain actually in terms of summary, the whole chapter 12, except one condition, that is the elasticity strain and stress condition, which we call the Young modulus application. Other than that, the whole chapter 12 actually right here on this summary. Okay, it's nothing much on that chapter at all. In terms of very different type of theories and things like that, nothing much there. It's a very simple chapter. So let's go into a simulator and then we'll start from there. You can find the simulator link on page number 2. Click on this arrow, then it will bring you to a page look like that. Then then click on the balance lab. There's 3 options. Click on the balance lab, double click. Then you are on this page, okay? On that page, you can see there's a yellow color item right here. And then you can see right here another yellow color, 2 V-shape icons. That V-shape icon is actually, we generally call the fulcrum, that actually the balance this horizontal line. Okay, the horizontal line is our meter rule. On your left hand side top, you will see different options. Mass labels, you can leave it there. Forces from objects, you can click that. Level, click on that. Then you will see 2 arrows appear. Those 2 arrows are actually telling you what's the exact horizontal line, like the x-axis, for example. Then below that, it says none right here for the position. Click on the ruler there. Select the ruler there. Then you can see a ruler will appear. Now this is not a normal meter ruler. You can see that one side, that ruler is length of the ruler is about 2 meters, right? It's starting from this midpoint, that's a fixed point. Earlier I mentioned that we're measuring now from the fixed point, okay? That's the interest. Doesn't matter where the fixed point is, you can put that according to the application. In this case, fixed point is here, so that we generally call the pivot point. So starting from there, right hand direction, I can go all the way to 2 meters. And the left hand direction, I can go all the way to 2 meters. This is 4 meter long meter ruler, okay? And you can see below here, there's 2 options right now. Left hand side option, click. Then you can see these 2 cylinders, gray color on there. And if you click the right hand option right here, then you can see 2 gray color cylinders will disappear. Okay? Click on that because we don't need that gray color cylinder to keep all the object. We need actually object to be freely rotate around the fixed point if there is a torque around fixed point. Now in this case, you can see object is at rest exactly horizontal because you can see these 2 endpoints are matching with the arrows, green color. So object is exactly on the horizontal point, so which means object is at equilibrium. Oh. Any question? All right, then let's continue. Now, let's take a look. If I bring the object, like previously I mentioned, if I bring this object and then place anywhere on the right-hand side, you can see object becomes unbalanced. The reason why the object rotated, this 5 kilogram create the force downward direction. That force is r distance away from the fixed point, which create the torque. That torque rotate the object. Now, if you take your right hand, there's two ways to identify the rotational direction and the torque direction. If you take the right hand, curl all this forefinger towards the rotating direction, then you look at the thumb direction, you will see the direction of the torque. Now, in this case, if that rotation happens, if the object has freedom of moving, this whole object right here, try to rotate and then move at the same time, it will rotate into the XY plane. That's the idea of the screw. If it is a screw, you rotate the screw into the clockwise rotation, the screw will starting to move into the plane. That is the screw tightening direction generally. Now, if I want to get this back into the equilibrium, I have to bring another object and then place somewhere on the left hand side. If I place somewhere on the 2, then you can see 2, it's the same mass, same 5 kilogram mass. However, since it is further away from the rotational fixed point, it actually creating more torque, because torque is r cross F, not just the force of gravity, r times the force of gravity, but the cross product. Because of now it creating more torque, now it is rotating more towards the counterclockwise. Now, if I bring closer, if I place exactly the same location as the right hand side, you can see object gonna go back into the equilibrium. When it exactly equilibrium, you can see these green color arrows starting to become green again. So that shows that horizontal yellow line, that's our meter ruler, is exactly horizontal. So then only we can apply that equilibrium condition, which means sum of the torque around this point P should be 0. So which means the torque coming from the right should be equal to the torque coming from the left. So that's the idea. What we're trying to do in this lab is actually investigate that behavior. Okay, any question? All right, then let's continue and then let's slowly discuss one by one. We're going to investigate like 3 different type of cases first by using the simulator. Then the last one is actually what we're trying to investigate. The data set is given already. So that part is we cannot simulate. So that data set is real in-class data set. So I will explain you what we're trying to do on that part after we finish the first 3 part with the simulator. Okay. All right. So you can take the simulator picture for the procedure section. You need just only one picture for the procedure section, right? So you can take the simulator picture for that and then attach that picture into here, this area. So that picture should go to the procedure section, and then later we'll take a few more pictures with the simulator, but those are actually data. Okay, I will show you what's the difference between those pictures and this one. This should show all this information, simulator information, all of this information, because that's our simulator which we are using for this one. That's for the procedure. But the later will take couple of pictures. You can see I leave the space right here. These are under this table. Those are actually data, okay, part of the data. Those should not go into the procedure section. Let's go and take a look the part 1. So in the part 1, what we try to understand is actually understand the equilibrium condition of the object by using the concept of torque. So to do that, we'll use one mass on the left right hand side, then we'll bring another mass, try to balance it. If I can balance it, I can understand how the torque is behave. I can calculate, for example, right side torque, that's clockwise, left side torque counterclockwise, we can check whether those two equal or not, right? So generally, if it is in class setting, we're going to get a percentage error between them. Since this is done with this part done with the simulator, you will get perfect result. Okay. So table number 1, mass on the right side, M2. So we can use like maybe 5 kilogram on right hand side, 1 meter location. Unit of that mass going to be kilogram. Let's use 5 kilogram. Right hand side, exactly 1 meter location. You can get rid of the other mass on the left hand side. And now you can see it is in balance. So if I want to level the object again, the meter ruler again, I have to bring another mass and then apply into the left hand side. So instead of bringing the 5 that's equal mass, let's try with the 10 kilogram. Okay? Let's bring the 10 kilogram and then apply that in left hand side. If I add the 10 kilogram very close to the pivot point, you can see object cannot level because the left hand side doesn't have enough torque, right? If I take that and then put it into 1 meter, then you can see it's too much because it's too farther away, then the torque is actually too higher. So it rotating too much into the counterclockwise becomes imbalance. But if I move in between, I can find a location, maybe it can level exactly. Still it too much at 0.75 location. But if I put it into exactly 0.5 on left hand side, you can see object going to go back into the level position. Arrows becomes green. So that exactly the position where object is at equilibrium. When it's become equilibrium, torque coming from the right hand side must be equal to the torque coming from left hand side. So that's what we're testing here. Very simple idea. So the position of the x1 unit meters, which is 1 meters, right? And the mass on the M2 unit kilogram. We are using 10 kilogram, right? And the position of that after it balance, then you found the position which is about unit meters, which is about 0.5. Now let's take a look at the torque. If it is really level, then we know torque coming from both sides should be equal, right? So the position of the position of mass M2 calculated and the experiment. So the experiment one, put it here. Then I will show you how to do the calculation. Okay. Put in the meters and the position we figure out experimentally 0.5. Now let's take a look the counterclockwise torque and the clockwise torque. Okay, if it is level, those two should be equal. And then the one thing I forgot earlier to mention is the unit of the torque. So how we define the torque. So we define the torque cross product between the radius and the force. Radius is measured unit of meters. Force is measured unit of Newton. Usually we just keep unit meter Newton for the torque. Okay, you know earlier, I don't know whether you should remember that anyway. So the unit meter Newton, if I write this oppositely, Newton meters, nothing wrong. Unit Newton meter is actually the joule, unit of work done. But do not write that unit here due to any reason, because to consider unit joule, I have to have the moving object. Object has to move from one point to another. Work done must be happen. In this case, there's no work done, okay? Torque can be there, but if object is not rotating, there's no work done. So the object must move to have the work done. Okay, because of that, do not write Newton meter due to any reason for the torque. It is meter Newton. Okay, how far away force applied from the fixed point that can generate possible rotation of the object. So that is meter Newton, not Newton meter. Okay, so do not write that due to any reason. Okay, so which means the unit for the torque is going to be meter Newton. And unit for the torque for this case, that also not millinewton at all either. So I would suggest just keep this space in between. The clockwise torque also should be meter newton, and the net torque also should be the same unit, okay, meter newton. And let's calculate counterclockwise torque. Counterclockwise torque coming from the 10 kilogram. Counterclockwise mean to the left relative to the fixed point, right? So which mean that going to be equal sign radius of the mass M2, that is this number 0.5, multiplied by force acting on left side, that is 10, and the side 90 is 1. We don't need to have that at all, equal sign. And I getting 5 meter Newton. And the direction of that we know, which is actually on counterclockwise direction. As a result of that, this direction is negative, okay? So I have to write this with the negative sign. So let's add negative sign here, or you can multiply this by -1. That negative sign tells you direction of that torque is actually towards negative. Sorry, counterclockwise is actually positive. So this should be multiplied by only +1, or you don't need to multiply at all, just leave it like that. Counterclockwise mean rotation is actually from your right hand side and then towards the left hand side. So as a result of that rotation, possible motion of that screw is actually coming out, right? Coming out the plane of xy, so that is positive z direction. Positive z direction means this number we just considered just a positive number. Let's do clockwise torque. Clockwise torque is coming from your right hand side relative to the fixed point, equal sign, radius relative to the fixed point right hand side, which is 1 meters, right? Cell number D9 multiplied by force acting on that direction, which is mass times the g. Okay, I actually forgot the g earlier. Mass times the g. I just write in the only mass here. Mass is 5 kilogram multiplied by 9.81. 49.05. So I need the same multiply g right here, 9.81, 49.05. So you can see that should be exactly the case. Both torque around fixed point should be exactly the same. Then only object can stay at rest. So that is called the equilibrium condition. Okay. So that two function which I using here. This is torque ECW, and this one is torque CW. Okay, question? Now let's take a look how we're gonna calculate this, right? Experiment the theoretically. So the calculation is already right here. We discussed earlier. So the calculation means you know if object is at rest or if the object is at equilibrium, then we can argue that sum of all the torque acting on the fixed point should be 0. So which means the net torque coming from the right hand side relative to the fixed point should be equal total torque coming from the left hand side relative to the fixed point should be equal. So in this case, I already fixed first object, that is to the right hand side, that is 5 kilogram of mass, 5.5 times 9.81 multiplied by 1.0 meters. Unit gonna be meter Newton, which must be equal. I'm going to try to put 10 kilogram on the other side. 10 times 9.81 multiplied by location of x2, let's say, I don't know. I need to find that out. I can find that location easily. I can find that location easily by just simplifying this formula, right? Unit going to be meter Newton, cancels out. And then I can find the location x2. 9.81 cancels out, 10 cancels out. Now 10 cancels out, this is 10, actually this is 1, okay? That should not cancels out. Get rid of that part right here. Okay, so my Excel sheet actually not responsive, it is stuck sometime. You see some delay on your side after I write, so I may have to close and then reopen it, okay? So you may see some little bit of delay when I explaining and then write it down, okay? Keep the x2 right here and then bring everything else to the other side. Then you simplify that one. 5 times 9.81 times 1.0 divide by 10 times 9.81. 9.81 cancels out. 1 is not important. 5 divided by half. So the half is about 0.5. Now this x2, which on your right left hand side should be about the half the meter. So that is the theoretical calculation, right? So that's what actually you've been doing in chapter number 12. That's where we are going to start. So we're going to bring this kind of ideas and then bring large object and then investigate this idea in detail analytically. Okay, that's a starting point for the PHY 294 class 2. And the only difference there, you're going to investigate a lot of larger structures, and then the free body diagram not going to be just this kind. It's going to be like very complicated type free body diagram. Okay? It has a lot of combined object together. You have to draw the free body diagram very carefully. Like for example, the structure of the home or the building or the bridge, you can see how complicated that is. That's the idea of that class, okay? All right, any question? All right, that means theoretically you just understand this one, and then after calculate, I know this should be in unit meters, and in theoretical calculation gave us exactly the same number as the experimentally observed one. So I can experimentally observe by just trial and error, moving the object mass M2 on the left-hand side, or I can investigate that theoretically by just using the torque equation. That's the idea. Any question? All right, so the clockwise torque is negative, right? I should multiply this by -1. If I add these two together, you will get the net torque equals sign sum of, you can say sum parentheses, sum of these two. So that will give you the net torque. Net torque is actually 0. That must be the case. If not, your object is not at rest. So we'll add that also here. Net torque, the command we are using. Any question? Okay, now this picture right here is actually the free body diagram, right? So which means that you have to get the picture after you balance this object, then take the picture. On that picture, we don't need everything. What we need is just the forces, and then we are acting on the object. Okay, so you can add that free body diagram into here. So my Excel sheet is actually very unresponsive. I may have to, let me give me a minute. Okay, I have to just close it and then reopen. Then it will be fine, hopefully. If not, I may have to restart the whole computer. Let's see. It will work. Let me check that. Yeah, that's fine now. All right, so let's add that picture here. So when you're adding that picture, you have to show only the free body diagram part. That means this component. Okay, crop that out. Anything unnecessary, we interesting only this part. Object and the fulcrum. Fulcrum is this stand and the fixed point and the two objects, and then you can see the arrow should be green, and this white arrow shows you the force. Okay, one is larger, one is smaller because it depending on the mass. However, the torque is actually equal. That's why the object is at equilibrium. Okay, that's the one has to go here. That actually data that should not go into the procedure section due to any reason. Okay. If you're doing in class, we actually drawing the free body diagram ourselves for this case. But since we're doing the simulator, we can use that picture. Okay, any question? All right, then let's take a look. It's a very simple calculation in terms of nothing much to do, calculation point of view. Let's investigate that for another case, right? To do that, I may have to use a different mass. We can use maybe for the case number 2, we can use 5 kilogram as it is, but maybe we can bring mass M2 instead of 10 kilogram, we can try that 20 kilogram. Let's see whether I can balance the object by bringing the 20 kilograms and then try to place that on left hand side. If I place it right here, you can see too much torque, leftward torque, too much counterclockwise. If I place it right here, it's still too much torque. So that means if you have too much torque, you have to bring the force acting point closer to the fixed point, right? And bring it more closer. Still too much. If I bring it to there, now you can balance it. So now you can see the masses, the object mass can be very different, but depending on how far away that force acting point relative to the fixed point, you may create the same torque, right? That's why the object is level. So that's all. Then we just need to complete this one. Case 2, mass M2 is the same. I have the 5 kilogram exactly same location, but the mass M2 now we using 20 kilogram. Position calculated will check in a bit. Position experimentally we figure out 0.25. We'll check in a bit how the calculation, and then we should get exactly the same number. We can take a look. So let's take a look at the theoretical value too very quickly. You know now how to do the theoretical value. Do it here now, case 2. Now you know sum of all the torque around point P should be 0. So which means sum of the torque around P right hand side should be equal to the torque around P left hand side. Right hand side I have 5 kilogram, 5 times 9.81 times 1.0 meter Newton. Left hand side I have 20 kilogram, 20 times 9.81 multiplied by, let's say the position of x2 I don't know. That's the one we need to find, okay? And the unit is Newton cancels out. You will get after solving unit meters. 9.81 cancels out. Then you will get x2, which is simply equal 5 divided by 20 and unit meters. So this is 5 times 1, 5 times 4, 1 over 4 is about 0.25 meters. So that's exactly what you get in experimentally, right? So that's the idea. So we tested experimentally, we got exactly same number. So our theoretical equation can be validated because experimentally we check that without knowing the theoretical value. Okay, we just randomly took the object mass 20 kilogram and then randomly we check different location until it level. So when it level, we know condition should be valid. This you can click and drag, it will do the calculation automatically, right? So this is going to be E12 clockwise, counterclockwise torque coming from the right hand side, mass 5 times 9.81 multiplied by the 1. And then clockwise torque should be negative coming from the right hand side. And the counterclockwise should be positive coming from the left hand side, okay? So if you do the calculation correctly for these three, click and drag, it will do the calculation automatically. Only the left hand side mass is different, mass and x2. That should give us the same number. Otherwise, object should not be level at all. Then you take the screenshot also. That screenshot must go here. Question. That screenshot should go. And also make sure be interested only that free body diagram part, how the object is level with applied forces on both sides. And now you know in terms of free body diagram is elongated, we interested the whole large elongated free body diagram, not like the earlier chapters. Okay, so that's our new free body diagram. Any question? All right, then let's take a look part two. Part two will try to do this study by using three objects instead of two. You can have many objects. In one side you have two, then I can balance that one, putting one another object into the other side. Or you may have two masses in both sides, but object is not level. Then I can bring the new mass and then add into the where what side has the lower torque, I can add the new mass, then I can level the object. So that's what we try to investigate on part two. So now in this case, meter is going to be at equilibrium. We try to make it equilibrium under three different masses. Okay. Again, the mass is measured in the kilogram. In this case, simulator actually can select persons instead of mass. We can use that here. So mass of the person on the right side, kilogram. Position of the person right hand side in unit meters. Person on the other side, unit kilogram. Mass and the position is unit meters. And then accordingly we'll calculate the torque under those two. And then we'll try to figure out theoretically and experimentally where the third mass should be placed to get that meter ruler into the level position again. Okay, that's the plan. What we're trying to do here is actually this. So we're going to place two different masses on this meter ruler. That's the fixed point. We're going to put one mass right here. Let's say mass M1. When one another mass right here, mass M2. Very different masses. And this will create downward direction or the clockwise direction torque. This will create counterclockwise torque. If these two are equal, object should be at level. If these two are not equal, object will rotate, right? I can find what is the torque counterclockwise. I can find what is the torque clockwise. Then I can take a look those numbers. If those two are not equal, then we know object will rotate. Then I can write, if I want to bring this back into the level position, then I know sum of all the torque must be 0 around the fixed point. Then depending on which one is lower, I may need the third force. So let's say third mass I am adding right here. Let's say that is M3. So the M3 will create M3 times G, downward direction will create the new torque on counterclockwise direction, torque prime. So then if object becomes at level, then we can say at this point, torque counterclockwise prime plus torque counterclockwise from the previous force must be equal to the torque clockwise. If that is the case, if I know what is the mass I am applying right there, I can find where it's supposed to go. That is the X3. That position I can calculate theoretically, and also I can investigate without knowing any of those formulas just by using the simulator. I can just randomly move that mass in and out until I see the equilibrium. That's what we're trying to do on the part 2. Any question? Torque unit again, meter Newton. Torque unit always meter Newton. And the torque balance, to balance the torque needed, that also should be meter Newton. And then the position I can calculate from theoretically and experimentally. We're going to try to balance it by using 20 kilograms. Okay? Let's take a look. Now the part B, instead of bringing the masses, let's bring two person. Person 1, 20 kilogram at X1 location. And then we're going to place it negative side to the fixed point. Okay. If you want to select the person, you can see right now the selection tool says the bricks. So that's only the masses. If you click this arrow right here to the right hand side, then you will see the persons. Okay. Person 1, 20 kilogram. Before you bring in them, you may need to get rid of these masses. Click and drag away. That will go away. Or you can click this icon right here, yellow button with the circle. That will actually reset everything. Let's bring person 20 kilogram, place at 0.5 location on the right, on the left hand side, negative x direction, 1 meter location. Okay. And then let's bring 80 kilogram mass and then place on positive x direction, 0.75 location. You can see 80 kilogram person is very heavy, and then he's a little bit further away from the rotating fixed point. So he creating more torque. As a result, object will rotate, right? So that is person 2. Now I need to balance this back. So you can obviously see I need more torque onto the left hand side. So to create the more torque, question asking you to balance level this by using 20 kilogram object. You bring the 20 kilogram object, try to place in different location. Let's place it right here. Not possible. Place it here. Not possible. Let's place it here. Not possible. Let's place it 1.25. Not possible. 1.5. 1.75. And then 2. If you bring it to the 2 meter location, you can see now there is enough torque on left hand side which will level the object again. When the meter ruler level, now you can say net torque comes from the right hand side now equal to the net torque comes from the left hand side. So we can do this kind of balancing with any different number of forces on each side. Okay. Any question? Person 1, 20 kilogram, location 1 meters. Person 2, 80 kilogram, location 0.75. Let's calculate counterclockwise torque coming from the left hand side before the other object put it in. Okay. Before this object place in, counterclockwise torque come in from the left hand side, equal sign. Left hand side is the person 1, mass times the gravity 9.81 multiplied by the radius r. That's the equation we need to get the torque. I'm going to place it right here. The torque counterclockwise. Okay. Torque CCW. Let's do torque clockwise before it balance. Okay, equal sign. Mass of the person 2 times 9.81 times position of the person 2. So that will give you torque acting on right hand side. That is a clockwise, right? Torque CW. Now you can see torque CW is very large compared to CCW. That's why object is in balance. Now torque needed to get this balance is actually addition of the addition of these two. If it is a 0, then it balance. If addition is not 0, then we can find how much new torque is needed. Okay. Now you know the clockwise torque is negative, right? I have to put that minus sign there. That negative tell you the clockwise direction, and then otherwise positive will tell you the counterclockwise direction. Now, generally, if I add these two, I should get 0, right? Let's add these two to see what number I'm getting. So equal sign, if you add these two, just sum these two together, then you will get minus 392.40. So which tells you negative 392 amount of torque is extra there on your right hand side. Negative mean right hand side, which means if you want to balance this, I have to have same amount of torque into the other side, left hand side, right? To balance the torque, balance the object, I need exactly same amount of torque, but the left hand side. Make sense? Following? Any question? Okay, let's go back and then take a look now. This M1 and M2 has to change, right? This one gonna be M1. This is X1. This is going to be M2, this direction, this distance M2, this is X3, M3. Now, torque counterclockwise is M1, X1 times gravity. Clockwise, M2, X2 times gravity. And then we know one is negative, other one is positive. If you add them together, I should get what's the net torque acting on the object, right? So let's add them together. Let's add torque clockwise plus torque counterclockwise. Then you will get M1 x1 times g, that is counterclockwise positive, plus M2 x2 times g, that is clockwise, that is negative, which is not now equal to 0. I will get a number, right? That number is the one you actually calculated earlier, 392.40. Okay? So that's the number we're getting earlier now. I have 392.40. That's the resultant torque. That resultant torque is negative, which means this is on clockwise direction. If I want to balance this, I have to add new torque on counterclockwise direction. That's why we need this M3 right here. So which means we can say, if I want to balance this again, torque 3 in terms of magnitude should be equal to this exact number, 392.40, but it should be on left hand side, right? This should be on left side. Now, what the question is telling, consider this torque is created by the mass M3, which is 20 kilogram, and then find the possible location X3. So then we can say, okay, so the torque 3 we know, M3G times the X3. That should be equal to this number, 392.40. Then to find the X3, all I have to do, 392.40 divide by M3 times the G. 392.40 divided by M3 is 20 kilogram, multiplied by G is 9.81. Then you do that calculation, then you can theoretically calculate what's the number we need. So let's check that out here, right? So the calculated value X3, we do now equal sign 392.40 divided by parentheses 20 kilogram multiplied by 9.81. So that's the location. So the location is exactly 2 meters, right? So that's the calculated value of what we're expecting. Now to investigate that, you get the 20 kilogram place in exact location, you will get object is level. So since we do in the simulator, then we will get the perfect result. If we do this in-person setting, if we testing that way, in-person setting, we will not get exact result. We will get little bit of error because that position of the object can be measured down to half the millimeter of accuracy with the meter ruler. Then we will get a little bit of error actually when we're doing such calculation. Okay. All right. Any question? All right, and also right here, torque needed to balance is actually not the negative, right? It is actually positive. I am taking the difference between these two, but I know it should be on left-hand side. So you have to get rid of that, okay? Get rid of the negative sign. You need to multiply by that negative one, because we know that number should apply into the left-hand side. Then that torque should be positive. Then only it balance, okay? I take in the torque difference, that comes out as a negative number, which means it is on right hand side, but I have to bring that same number into the left hand side to make it balance. So I have to multiply this by negative sign, and then we know theoretically it becomes true, and also experimentally we tested out that one. So the torque balance, that's the torque needed, and the calculated value by using the mass m, that is position of x3 of mass m3. All right, any question? And you may need the screenshot of this one again. That should go here. Insert. Rid of this. Okay, and then you have to show the force vector completely. Okay, right now you can see force vector is much larger. So I'm going to leave it like the thing right here. Otherwise, I can't see the size of that force vector. Okay. And we can check this with other type of masses available on here. If you get rid of all of these persons and the mass, then you can click the right arrow right here, then you can select the different persons. So instead of 20 and 80, maybe we can use 20 and 60, and then we can take a look how to balance that. Okay. So let's bring 20%. You can leave it right there, 1 meter. Instead of 80 kilogram person, let's bring the 60 kilogram person and then place on 0.75. And then let's do the calculation again. Person one, you can even try different masses, doesn't matter. Okay, you can bring this person, 30 kilogram person if you want, doesn't matter. Okay, 20 kilogram person one, location 1 meters. You can change that location too, but the idea should be process. Okay, person two now 60 kilogram, position of the person 2.75 is still. So these values, actually you can click and drag. That will do the calculation automatically. Let's try this one too. So I need 20 kilogram at 2 meter location, right? To level this one. So let's check this one. Oh, that click and drag will not work. You have to correct that out because I'm not using cell values. So I'm using the numbers, okay? So actually you can correct this with the cell values if you want to. So the best way is that click here, delete that, and then select the cell value and then divide and hit enter. Then click and drag. Let me copy that function and then right here. Now I'm using the cell value, okay? All right. Now you can see, then if you click and drag, then it will do the calculation correctly, because earlier you can see immediately it's the same number. That impossible because I changed the person to mass. I can't have the same place as for the previous case. It should be a new number. Now you can see it's a different number. Now we can test it out. Let's take a look by using the 20 kilogram object. If I put here, not enough, not enough, not enough. If I bring into 1.25, it can actually level. So our calculation is exactly correct. So what we're testing here now, torque balance equation. and the idea of the torque, rightward direction, leftward direction, and the equilibrium of the object. All of those concepts can be validated by simply doing this simulation. Okay. All right. Any question? Let's take a screenshot of that one too. Should go here. Make sure we interested now only this free body diagram, which means all the forces should be visible. You can see that force arrow. If the object is much larger, force arrow is larger, so I'm going to leave it that part is visible. Okay. All right. So by now you should complete whole table number 2. Then only 2 parts to go. That's fairly very simple. We can still finish, I think, before the time up. Let's take a quick break here. Then we'll start in 10 minutes. Okay. All right, now next part, so far what we done, we tested out the torque equation, torque balance by using 2 objects, both sides of the fulcrum, and then we try the same idea, torque balance equation by using 3 objects, 2 objects on one side and 1 object on the other side. And then let's take a look the same condition whether we can apply to figure out unknown mass. Okay, that's the plan for the next condition. So which means, let's say for example, I have a mass, a object right here, object A, mass is unknown. So I want to find that mass, right? So I can simply use this idea which we actually doing so far. So I just need the meter ruler and the fulcrum. So we're going to first balance the meter ruler around the fixed point. After I balance the meter ruler, what we're going to do, we're going to bring this unknown mass and then place on one side. Let's say unknown mass, I place it here. That is mu, and then x of u, we're going to know that because that exact this location, right? So this is going to be mu times the gravity force of the unknown mass. And now this will create torque around the fixed point and then right hand side direction. As a result of that, object will rotate and then go into some sort of inequilibrium point like that, right? I can make it to equilibrium again by placing the new force, new object somewhere here, known object. Let's say this is m1 or m. We know the value of that, like 20 kilogram, right? So let's bring the 20 kilogram. Let's check the position, right? So let's put it very end point right here, somewhere in the middle, very close right here. Let's take a look which place it's going to bring this object to the exact level position. Whenever the object becomes level, let's figure out that position. Let's say that is x from the fixed point right here. This is going to be mg. Now you can see object is at level. So object experience torque CCW. That is the torque around fixed point from the left side. Torque CW, that is the torque around the fixed point from the right hand side. When these two are equal, object is at equilibrium. Very simple idea, right? So then I can simply say sum of all the torque around fixed point should be equal. Now I can say sum of the torque around fixed point from right hand side should be equal torque around fixed point from the left hand side. From the right hand side, I have x of u times m of u times the g, which is equal left hand side x times mg. So g cancels out. I can find the mass unknown, which is simply x times the m divided by x of u. And the unit of the x cancels out, unit going to be end up as the kilogram. So very simple idea. So which mean I can find the mass of that's how actually, for example, standard kilogram or any other standard values is defined, right? So you have a piece of gold or particular object. Long time ago, hundreds of years ago, people agreed on that's the amount of 1 kilogram. That's it. That point and onwards, relative to that kilogram, what we agreed on, everything we measured as 1 kilogram, 2 kilogram, twice of that, 3 kilogram, 3 times of that, and then half the kilogram, half of that, and then so on. That's how we started. Now, for example, if I want to find the standard 1 kilogram relative to that object, what I have to do, I just need a object at equilibrium. Let's bring the standard kilogram value and then place it here. Let's say this is a standard kilogram value. Let's bring another object, another mass right here, and then change that mass until this become equilibrium. When that happen, we can say exactly this mass is equilibrium 1 kilogram. However, this should be at exactly same location. If the location changes, then torque equation adding extra component from the distance. So the distance should be cancelled out. If distance cancels out in this equation, you can say mu is equal M. So I can standardize any weight of any object accordingly. Okay, so that's the idea. Question. All right, so the position of the unknown mass measured in unit meters, mass of the left side unit kilogram, mass of the position of the mass in which is the known mass unit meters. Counterclockwise torque, you know the torque units is meter Newton, clockwise torque meter Newton. Unknown mass, we can use the same unit kilogram. We can find it by using the torque balance equation, right? Kilogram. Now we'll do this for a couple of different objects. If you get rid of all these items and the persons on the object, on the meter ruler, if you click this right arrow, if you click this 3 times, then you will go into a point where it says mystery objects. So there's 4 type of mystery object, A, B, C, D. So we'll bring it one by one. Those are these cases, okay? Case A, case B, case C, case D. Those are for those objects. Let's bring those objects one by one, balance it by using 20 kilogram object in the other side, and then we'll use the torque balance equation to figure out that mass of the unknown. Okay, that's the plan. Bring object number 1, place it 1 meter location right here. Position of the unknown mass 1 meters. So let's bring 20 kilogram and then try to place it on other side. If I place in 2 meters, too much leftward torque. If I place it on 0.25, too less torque on the left hand side, which mean in between I should be able to find the location. Now I'm not doing theoretically, okay? I'm completely doing this experimentally. I could calculate even, you know the equation. So let's slowly move this little bit higher radius. When it is exactly at 1 meter location, you can see meter ruler becomes level. So which means mass on the left hand side 20 kilogram, position of the mass of the left hand side 1 meters. So which means you know theoretically what should be the formula is xm over xu. So it should be just 20 kilogram. And then experimentally also, you see that should be exactly 20 kilogram, right? So the torque clockwise equal sign. Clockwise mean mass unknown x of u. You need to write it down, just the formula there, okay? Mass unknown x of u multiply by the distance for that mass 1 meters, okay? 1.00, and sorry, the counterclockwise. Counterclockwise is mass known, which means mass of m multiplied by position of that x. Let's write it down, that equation there. Mass of m, position of x, mass of m 20 kilogram multiplied by position, in this case 1.00 meters. And if I do that same calculation for the clockwise, equal sign, mass unknown, x of u multiplied by, get rid of the equal sign because I can't do the calculation, I just write in the formula, x of u multiplied by 1.00. Now these two should be equal, right? So that's the idea. By making these two equal to each other, so I can find the unknown mass xu. Now if you do equal that, there's nothing to calculate. Unknown mass is just simply 20 kilograms. So that's the idea, okay? Any question? All right. Then let's check the same one with a different mass. Let's get rid of object A, and then let's go into the unknown masses. Let's bring the object B and then place in the same location. If I place object B on the same location, you can see now there's too much torque on the other side due to 20 kilogram, right? So you have to change that location. So if I bring it to 0.75, still too much. 0.5, still too much. 0.25, you can balance it. Okay, so which means the position of the unknown mass is still, I'm going to keep it 1 meter. Mass left hand side 20, but the position of the mass left hand side now 0.25. Okay. Now these two, it's the same except one number, that is this position, right? Position of the known mass is 0.25. Now these two should be equal to each other. These two should be equal to each other. Right? If you make this equal to each other, then 20 times 0.25 should be equal xu times 1. So the xu going to be just simply 20 times 0.25. Right? So you can calculate that. That's simple calculation, just 20 divided by 4. So you can calculate that by using 20 mass of the known times radius for the known mass. That should be 5 kilogram. Object number B should be just 5 kilogram. Question. And then likewise, we can continue. There's like many different unknown masses here, but let's try 2 more. And also each case I have to take the picture, right? So I should actually get the picture for object A also. We know the location exactly. A screenshot after it leveled. And also I need the picture with the object B. We know the exact location now. You have to take the screenshot after it level. Those two should go here, okay? Top balance picture. Insert pictures. Picture for case A first. Get rid of these. I just need this free body diagram part only, okay? Not anything else, just this part. Right, this should go here. That for the object A. And then let's do object B. Any question? It should be very straightforward experiment, nothing much to do in terms of calculating or anything. Only the torque balance equation. If you understand that torque balance equation, then it's very simple things we do in this experiment. Okay. All right, then let's take a look two other cases. Object C will place in the same location, 1 meter, unknown object. Known object will still use the mass 20 kilogram. Now you can see not enough torque. Let's bring it to the 2 meters, too much. So which means in between. I can calculate, but I'm going to do this trial and error way. Just change the position until it really level. When it's level, then we know exactly the torque balance should be valid. Now the position is 0.75. So these two are the same formulas, but you have to edit the numbers. Okay, the mass 20, but position is 0.75. This one is unknown mass is still at 1 meter location. So which means the unknown mass should be now equal the mass of the known 20 multiplied by position of that mass 0.75. The magnitude of the unknown mass should be about 15 kilograms. Let's take the screenshot. Any question? Okay, then let's take a look one other case. Then the last part is actually we're going to do by using the in-class dataset. Okay. Right. Last case, let's bring the other object, object D. And see if I move the 20 kilogram into 0.5 location, it will balance perfectly. Take the screenshot. That should go here. And by now you know how to do the calculation. Okay, we need just the river diagram area right here, only that part we're interested, and then bring it to the right location right here. All right, so let's do that calculation. So what we have, the position of the unknown object D, we're going to keep it the same position, 1 meters, mass known 20, and when it is level, position is 0.5 meters. In terms of two formulas which we're working on, left hand side 20 kilogram times 0.50 and should be equal to the XU times mass of U times the position of XU. So this right here should be MU, right? Because that's the one we try to calculate. Please correct that. So I mistakenly put it there. X of U we know, but we don't know is the mass of unknown. That should be M of U, okay? It should be M of U. Otherwise, everything is fine. And we know now because of that two formulas should be equal to each other. M of U should be 20 times 0.5. Then you will get the answer. Equal sign mass known multiplied by the position known on left hand side. It should be about 10. So in terms of function right here, you just can actually do that calculation what you've done here. So this also going to be a function then, mass known multiplied by the position known. Those are the four functions. You can just copy paste those two, very simple calculation, nothing much to do. Mass unknown for case A, And then same for mass unknown for case B, case C, and then case D. It's the same kind of function. Okay, you can copy paste all of these functions. Okay, any question? All right, then let's take a look last part. So on the last part, what we try to do, we try to do a little bit of different idea by the same concept. Okay, so what we try to do there, we can't actually use a simulator. That's the problem. Now we try to change the fulcrum point. That's the pivot point. Okay, so which means the simulator doesn't allow us to change the fulcrum point. Okay, so that's why I have to use the data flow coming from the class setting. Now earlier, let's say if I have a meter ruler, if I balance the meter ruler exactly, it's center of mass point. Now you have idea about center of mass point, right? Center of mass point is the point where the total mass of the object looks like acting on one object. Technically, the mass is distributed over 1 meter. But if I can balance the object in one particular point, which means that point look like total mass, total gravity, gravitational force acting on that particular point, that's the center of gravity or center of mass point, right? So if I have the fulcrum point right here, that's the pivot point, object will level, object will balance. There's no rotation at all. But if I move the fulcrum point to a different point, now let's say if I move I keep the same meter ruler, and this is where the center of mass point is. Now I know that should be the gravitational force acting location, right? So the gravity will be acting on exactly this point. That will be the mg, let's say large mg gravitational force of the meter ruler. Now I'm going to move this fulcrum point a little bit towards my left hand side. Now I'm going to place that fulcrum point right here. That's the pivot point. Okay, it's a fulcrum is the stand where you can balance the meter ruler. Now you can see if I try to do that. Now let's say this is x0, which is the standard center of mass point. So that's about 50 centimeter location. Now if I move into the little bit further away, that is x0 point. Now let's say this is the new fulcrum point, x0 prime. Now you can see this force right here, try to drag the object downward direction. It will create torque around the fixed point right hand side. That is actually the torque W, which is negative, right? Which is a negative number. Now because of that rotation, you cannot balance this object, this meter ruler this way. If you try to balance it, it will fall down. However, if I can bring another object, another mass, and then put it on the other side, I can still balance the meter ruler. Which means, if this is an in-class experiment, this is what we're going to do. We're going to put a hanger on this side, and then we're going to add hanger itself about like maybe 50 gram, and then we're going to add slotted weight, small circular weight pieces. We can put that into the hanger. Okay, those are called slotted weight. So we're going to add that slotted weight slowly, like maybe 10 gram at a time, 5 gram at a time, and then so on. We're going to add it slowly until we're going to see this meter ruler becomes level again. Okay. So it's difficult to do if this is an in-person setting. This part of the lab is actually very difficult because the finding that exact level point is not easy. Any small movements, if you even walk around that table, any small movement coming from the air oscillation even becomes this imbalance. So any of those things, if you touch the table, that vibration make it imbalance. Very difficult to find exact balance point. If you don't have exact balance point, then our next calculation going to be very inaccurate. So the error going to be too high. So that's why it has to be doing very carefully and smoothly, then you will get the right answer. So which means when I adding the mass here, I have to be very careful. Then after it balance, let's say total mass right here is m multiplied by g, I will get the force of gravity there. Now this force right here is invisible now, right? This part, you're not going to see anything there because that is acting on that point. But if you look at that system, you're not going to see actually anything there. If you're doing this in-person setting, that is how it looks like. So there's nothing here, but that invisible force mg is actually already there because that is the total weight of the object. That confirm another way center of mass point of the object. If you do this experiment, what it confirming actually total mass of the object acting on one particular point, that's the center of mass, that also confirming. It not only confirming with the previous balance, this will confirm definitely it acting on that point. Now, all I have to do, this distance I can find, right? This separation, and I can find this separation. Let's say this point is x. So if I know those two separations, then I know these two forces. Then by using that, for example, I can estimate mass of the meter ruler. That's the plan. So to do that, what you have to do, you have to write now force balance, torque balance equation. Sum of the torque around 0.3 must be equal 0. Now let's write it down that I have torque coming from around P from right hand side plus torque around point P from the left hand side should be equal to 0. So torque coming from right hand side is equal separation between the force mg, separation between the force mg and the fulcrum point and the magnitude of the mg. Separation is, I can write x0 minus x0 prime. And minus sign, this is actually minus, plus small mg parentheses x0 prime minus x, separation between the small mg times the new fulcrum point P. Now all of these should be equal to 0, or you can simply say these two are equal to each other. That also same. Earlier we always writing those two are equal to each other because of this. Actually this is going to be a negative number, negative PR plus torque PL equals 0. That's why earlier we usually write this way. So always torque coming from the right hand side is equal to torque coming from the left hand side. Okay. But technically one is positive, one is negative. You add them together, you will get 0. That's the idea. Okay. Question. Now if it is in-person setting, usually x0 going to be about 50 centimeter location, right? And then x0 prime, we can say 30 centimeter location. I'm going to bring that point a little bit towards my left hand side. If this is 0 starting point of the meter ruler, if this point is the 100 centimeter location of the meter ruler, because it's 100 centimeters long, 50 centimeter was earlier I keeping my fulcrum point. Now I bring it towards left hand side, little bit lower than 50 centimeter. Okay. We can go different numbers, but the data set I have is actually with these numbers. Okay. So which means I know those two, this and this, and the x gonna be now is actually new value after it balance, right? By knowing all of this, and then the amount of mass also we know how to balance it, and then by using this equation now I can calculate mass of the meter ruler is equal just simply mg times x0 prime minus x over x0 minus x0 prime. All of numbers we know, I can simply calculate it very easily. Okay? That's the plan. Now, if I do this one time, I can do it, that's fine. But I can do by changing this, right? For example, I can shift this one slowly into a different location and then try to rebalance. And then shift this into a different location, I can rebalance, okay? As a function of that, as a function of shifting x, I can actually find amount of mass I need to rebalance this, right? If I do this again and again, by changing those two, I can use same formula, but I can do the graphical method. So which means x0 prime minus x is equal m times g times x0 minus x0 prime times 1 over m. So which means if I rearrange the formula, this is the mass needed to balance. This is what I changing, right? Position of the hanger. Everything else we know except this guy. So which means if the position of the hanger is different, I need the different mass. So likewise, I can actually get a data set. So my data set gonna be then 1 over m is the x. This part right here is the y. If I make a graph, this gonna be y equal ax type graph. Now this whole part gonna be the slope of the graph. Okay, sorry, I missed, did one mistake earlier. This g can cancel out, right? We don't need to have it. On the formula, we can get rid of. We can keep it, but what is the purpose of keeping that something which is actually can cancel out in the equation? We don't need that. So which means if I make a graph, that graph gonna be simply 1 over m, 1 over kilogram versus x0 prime minus x. This is going to be unit meters. That's going to be simply a linear graph. By taking the slope of that linear graph, slope will be the a. A is equal m times x0 minus x0 prime. These two we know. Okay, one is 50 centimeters minus other one is 30 centimeters. I need the unit in meters multiplied by -2. That means about 0.2, right? So which means simply I can say mass of the meter ruler is equal slope divided by 0.2. So if I have the slope, then I can divide by 0.2 to get the mass of the meter. So that's actually the major part of the experiment. That is actually more focused in our in-person experiment. The reason that take actually a lot of time. The everything else we done with the simulator is fine, but in terms of real experiment, that is actually our main concern, main part if we're doing this in-person setting. So now, since we can't do that, what you actually see here is the data set. So what this data set shows you in table number 4. So the mass M1, which is actually the mass M which I wrote earlier on the left-hand side with the hanger. So by changing the mass, you can see I'm changing very small, okay? This is in unit kilogram. So I'm changing about like at a time 20 grams, very small amount of mass. When I change that, you can see I need the new position to level the meter rule. And then you can see the position is actually changing slowly as a result of changing mass, okay? So that's the idea. Since I know these two, I know the x0 and x, then I can simply do that graph and then try to figure out the mass of the meter ruler. That's the plan. Okay, any question? All right, so to do that, we need the x0 minus x1. x0 is 50 centimeter. That's the center of mass point. Going to be equal sign 50 centimeter means 0.5 minus x1. We have to do that calculation here. Of course, we need that to do the graph. It's going to be then x0 minus the x1. And then I can calculate the mass of the meter ruler before I do the graphing. Then you know meter ruler. Mass going to be equal mass times x0 prime minus x divided by x0 minus x0 prime, right? Now this one right here should be x0 prime. Actually, there's no meaning writing x0 minus x1. I need the x0 prime x1. I think there's no way to put the x0 prime there. That's why I missed that. So there's a way to put the prime. You can actually do this way if you want. That way is fine. If not, you can actually insert the equation. Okay, insert symbols equation. Then you can write nicely those the formatted equation. Like for example, if I wanted to do different equation formatting here. You can see different formatting. If I want the prime here, you can select that. Then I need, let's say, x0 and then the prime on top. Now you can see it's a very nice format. Okay, so that may be the best way to do, but if you can't do it, just type x prime and then parentheses 0. That's okay, I think. Then minus x1. If you type this, that's going to be looks nice. That's the only difference. Okay, x1. And I can actually use that in here. Okay, that looks nice. Otherwise, if you can't do that way, just put the 0 inside the parentheses. Okay, general typing. And I need that to make the graph, right? X0 prime minus x and also 1 over m. So let's calculate that also, equal 1 divided by mass of the hanger. Click and drag. It should be x prime 0 then. And also this is the function I'm using, 1 over m. Those are simple things. I think by now you guys know how to do these things. Now let's take a look. I can do the graph very easily, but let's take a look. I can calculate the meter stick mass, right? Because I have the formula, right? You know the formula. You can do that calculation easily. Let's do that too. So the formula is mass of the hanger, x prime minus x divided by x0 minus x prime, right? So let's do that. Equal sign mass of the hanger multiplied by x prime minus x, that is cell D69, divide by x0 minus x0 prime. So x0 minus x0 prime means x0 is 50 centimeters, 0.5. x0 prime is the new pivot point, that is about 0.3. Then I'm expecting about like 137.8. Okay, question. Let's see, that too high according to my memory. So I did a mistake earlier there because x0 prime should be actually 30 centimeters. Let me add that numbers here, otherwise you will get that confusion too. Let us add that two numbers into here. Okay, so x prime 0 should be about 0.30, 0 in meters, and 0 should be about 0.500 meters. Okay. Since you're not doing in-person settings, so those two numbers you should know because you can have that mistake here. Please correct that, otherwise our calculated value will be incorrect. x0 prime is the new pivot point that should be towards left, the center of mass point that should be less. Okay. Now we good. When you click and drag this, then you will get mass of the meter ruler should be about the same because we're not changing anything there, right? Mass of the meter ruler should be about the same. You can see it's changing around 0.07, that means about 70 grams. This meter ruler, what we're talking about here, is actually the wood meter ruler. I think you, whenever you go into a physics lab class, you can take a look. There's like bundle of meter rulers there. Those are very light, so about like 70 grams or so. Okay, so it changes slightly. That because of our reading error. Otherwise, it is perfect data set. Okay. Any question? Units here gonna be 1 over kilogram. Okay, then let's continue now. All we have to do, make the graph, because we earlier mentioned that I can calculate directly. Of course, I have the formula, but if I have data set, I can actually take a look that in terms of graphical nature, right? That's what we're doing in this class, right? Most of the time, we take a data set and then we investigate the data set by using graphical method, right? So let's make a graph. So insert, scatter plot, these things you know now, right? It's not a big deal. We're doing this now many times over the semester. Double click, select data, and then let's add the data. Y column, X column should be 1 over M. Cell values F70 to F74. Y values should be X0 prime minus X. So that is D70 to D74. Click OK. Click OK again. Then you will get the graph. Nice linear graph. Okay. And everything else, you know now, if you have a graph, you have to make the name, right? This is what 1 over M1. This is X prime of 0 minus X1 versus 1 over M1 4-meter ruler. If you have a graph, then double click, chart elements, you have to put axis title, horizontal, vertical. If I have a data set linear, I would like to have the trend line, chart element, left hand side, very top, chart element, linear. And then you may have to do a little bit of editing here. So axis title, X axis going to be 1 over M1, right? 1 over M1. It's going to be 1 over kilogram. And the Y going to be X prime 0 minus X1 minus X1, and then unit should be meters. Right, so we have the graph, we have all the formatting done. The only thing is remaining is that if I want to get the slope of the meter ruler by using the graph, the mass of the meter ruler by using the graph, I need the slope of the graph, right? To do that, all we have to do is to show the equation of this fitting, right? So the fitting line is dotted line, double click on that, then go to the very end of your right hand side new menu bar and then click all of these three. So that will show you a number in front of X, that is the slope of the graph. That's the one we need. You can see R is equal 1, so which means our data set is perfect. Okay. If you have a figure, you know you have to rename it as a figure in your report. So it's better to name it here and then bring it there. This may be then figure 2 because one figure going to be onto your procedure section, right? Since we're not really doing the in-class experiment, you don't need to worry about in-class diagram or usually we take the picture of our apparatus after we set it up. So those things you don't need to worry. Okay, you can just briefly mention, because I think in your lab manual I leave it all the apparatus needed for the in-person setting. Even the procedure part, you don't need to write in detail there. Okay, in terms of procedure, you have to write in detail only this part. Okay, simulator section. This part you don't need to worry about writing the procedure. You can include that, and then you can mention the last part we investigated by using the real experimental data set, but we did not perform that. You don't need to write the procedure section at all. Now this is figure of what X prime 0 minus X1 versus 1 over 1 for meter ruler.
Professor.
Yeah, what's up?
I have the exact same values as you on the table, but my graph Y value is completely off.
Then you select the different X and Y values here for the graph. You have to go back to the data section and then click on series 1, click edit, and then delete everything on the X and the next should be this column, okay, column F 70 to 74, okay, and then delete everything on Y should be column D 70 to 74. So sometime it can flip, then your whole graph going to be very different and the numbers going to be wrong actually. Any other question? Right, then that's it. Then let's take a look. The last table, that's a percentage error analysis. We calculate the mass of the meter stick. You can see different data point. If I have a few different values, you would always like to take the average, right? So this is unit of kilogram. Let's take the average here. Equal average. And then the average of E70 to E74. That's the MLAVG, mass of the meter ruler, calculated average. I can find the mass of the meter ruler by slope of the graph. You know, earlier from the equation, slope of the graph divided by 0.2, right? So let's check that. Slope of the graph is about what? 0.0143 equals line slope of the graph 0.0143 divided by 0.2. So we're getting about the same number, only the third decimal place is different because data set is actually too good. But if you're doing this in person setting, you're not gonna get that much accurate data set at all. We usually get fairly decent error actually in this kind of calculation. Okay, fairly large error we usually get in because that balancing point, it's very difficult to find to the very accuracy. So because of that, usually about 10 to 15% error we usually getting in this part. Question? Since we have two data points, so two values for the same thing, let's compare them. If it is in-person setting, we actually measure the mass of the meter ruler exact value by using the balance. Then we're going to compare percentage error for both of this. Since I don't have that number, let's compare these two percentage difference. Okay. Equal ABS parentheses, calculated average minus value from the graph, close bracket divide, calculated divide parentheses, calculated average plus from the graph, divide by 2, multiplied by 100. Doing percentage different, not the percentage. You can see it's a very small value. Reason this data set is actually artificially created by using the in-person class data set, but I artificially edit that to get it a fairly accurate value. That's why otherwise usually it's going to be very large error. Okay, any question? All right, so that's about it for this lab. You can see it's nothing serious lab, but still we can learn a lot of things, right? We learn about the equilibrium condition. So the Newton laws itself not enough. So I have to take a look the extended version of the Newton laws. That's the rotational version. So I take a look the rotational version of the Newton law, the torque, and then we use torque balance equation to understand the equilibrium of the object. And then we measure even unknown mass. And then we use the same torque balance equation to figure out the mass of the meter ruler by using the experiment, which is very similar to the torque balance experiment we done with the simulator. But the new method is we shift the pivot point into a different point than the center of mass point. Then we actually use that method to calculate the mass of the meter ruler itself. Okay. That's what we done. So by now we should have everything completed. So we have few minutes. So we can go and take a look the last chapter, and then because that chapter there's actually another section. It's a long chapter. Both of chapter number 9 and 10 both are very long. Let's look at least one question from there. Anybody have any question?